Hello and welcome back to another multivariable Calculus 3 video. Today we will be going over partial derivatives. So, what exactly is a partial derivative? Well, let's think back to Calculus 1 and 2. In Calculus 1 and 2, the derivative calculates the instantaneous rate of change for a single variable function, while a partial derivative measures the rate of change of a multivariable function, which essentially is fancy word for we're holding the x or the y or the z constant within a function, and then we are taking the derivative in one way. I will get into this more when we talk about the y, but as for right now, the what? A partial derivative measures the rate of change in a multivariable function. So, I suppose the y, as I stated before, in Calculus 1 and 2, the derivative calculates the instantaneous rate of change for a single variable function, such as the derivative in terms of x, the derivatives in terms of y, whereas a partial derivative measures the same rate of change of a multivariable function relative to one variable while holding all of the others constant. What you may be asking is what the difference between those two is. Well, the standard derivative that you may have learned in Calculus 1 and Calculus 2 evaluate the change in one dimension. Partial derivatives isolate the change along a specific axis, y, x, or z, within a multidimensional space x, y, z. It's easier to comprehend than it is to explain, so let's just go ahead and look at the Calculus 1 and 2 picture. Say we have some kind of function here. The rate of change at some value a, let's go here, b, would be the derivative at that point. So it would be just like that. The line tangent, okay? Well, let's go ahead and do one more. We have C and D right here. We have that tangent line right there. Those are essentially what the rate of change is in a one variable sense. Well, coming over to the Calculus 3 picture, we have a three-dimensional function, right? Well, what if we wanted to find the, let's just say, the slope only in the x direction? The slope of this function only in the x direction. Well, how are we going to do that? I'll spoil this one over, the answer over here a little bit. We are going to be holding the y constant. So our x is variable, whereas our y is not. Therefore, this little green line right there, that is z is equal to f of x at some value d. You could also think of it as a y is equal to b trace or d trace, something that we learned in quadratic surfaces. So let's just say we wanted to take the instantaneous rate of change at the point CD. What would that look like? Well, that would look like the tangent line holding y constant. The same thing works for when you're trying to find the slope in the y direction. The slope in the y direction is what? Well, we have this function wherein we keep our x constant. So we have a function of a, y, a being this right here, and our d being this over here. Well, what would that look like now? That would also look like the tangent line to the curve, to the trace. The x is equal to a trace. That is essentially what the picture of a partial derivative is. It's a fundamental topic within Calculus 3. It's something that you are going to be doing constantly. So I guess the question that we are asking is, how do we do it? Well, essentially how we do it is we derive in one variable and hold the others constant. So one of the pictures that I am just going to draw here, say we want to find the partial derivative of f with respect to x. Well, this essentially means that we are going to have x be its variable per usual, whereas we treat the y or the z, whatever other variables are in the equation, as numbers. So one of the best ways that I can really do this is to just give you a function and tell you how I might go about doing that and how I might go about visualizing that. So let's just say we have some function xy wherein we have x squared plus y squared. We want to find the partial derivative of x, and we want to find the partial derivative of y. Well, how are we going to do this? We're going to take the partial derivative in terms of x squared plus y squared. Well, conceptually, what are we doing? We're taking the derivative in terms of x while holding the y constant, meaning what? I personally like to think about this like, it may be easy to think about it like this. X squared plus 1 squared. How would you take the derivative of that? That would just be 2x, right? Well, let's go over here and do the exact same thing. We take the partial derivative of f in terms of y of x squared plus y squared, which is going to equal what? Well, let's just think about it. If our x is a constant, then it's the same thing as 1 squared plus y squared. What's the derivative of that in calculus 1? That would just be 2y. That is the easy picture, in my opinion, is just think about it as a constant. We are, like I said, setting our z equal to f of some function wherein one of those variables is held constant. That is the easiest way to think about it, I think. So that is essentially what a partial derivative is. I'm going to be getting into more explanation of what it is, but I would love to go over some notation first, because there is a lot of notation for what a partial derivative is. Now, in the calculus 1 and calculus 2 picture, the derivative was d over dx, or d over dy. In Calc 3, we use our partial derivatives with this little squiggly d, I like to think of it. So we have like a little squiggly d wherein it is a partial derivative, and compared to the single variable, it is just a regular d, right? So partial derivative notation may go something like this. This applies for x and y as well. We have d over dx of f, which is also equal to f sub x. I like this notation the most. I think it is the most simple. Some other ones that you're not going to see nearly as often is the derivative of x in f, or d1f, or f1, or you could go on. But the main two you're going to see are here. These two are your main ones, and that applies for the f, or the f of x and the f sub y. That is some notation. Let's just go ahead and dive into some examples. First example, we are going to want to find the partial derivatives of f of xy is equal to 4x squared plus 3y to the third. Well, what is our f sub x? Well, f sub x is taking the partial derivative of this function in terms of x, 4x squared plus 3y cubed. Remember, we can conceptualize this as 4x squared plus 3 times some constant, I'll just say 1 cubed. What is the derivative of this going to be? It's just going to be 8x plus 0. Well, let's go ahead and do the exact same process for f sub y, the partial of y. What is this? The derivative of x, the partial derivative of x, or the function in terms of y. So we have our 4x squared plus 3y cubed, which is going to equal what? Well, let's just go ahead and set our x equal to some constant. 4 times 1 squared plus 3y cubed is essentially what we have. Just using the power rule, we have 9y squared. That is our answer for the partial derivatives of these functions. For the next one, I am not going to be conceptualizing it like that. You get better at it as time goes on, is all I can say. You will not have to think about it that way. You will just see, oh, I'm taking the partial derivatives in terms of x. That means I only derive functions with x in it. Everything else is like a number, equals 0. So let's just go ahead and do one more problem. Let's do a little bit more difficult one. Given our f of xy is equal to 4x squared plus 5x cubed y squared minus 9y to the fourth. Well, let's go ahead and find the partial derivative of x. Okay, so we're asked to find the partial derivative of f with the terms in with respect to x of 4x squared plus 5x cubed y squared minus 9y to the fourth. Well, what is this equal to? We integrate aspects with x in it, or not integrate, we derive aspects with x in it like we normally would in calculus 1 and 2. So we have our first one, power rule, 8x plus 5x cubed y squared. What does this mean? Think of that y squared as, like I said, another number. So we have 5 times y squared times x cubed. What are we going to do? We're just going to take the power rule, ignore the y for right now. So we're just going to have 15x squared y squared minus 9y to the fourth. That's just minus a constant. That's going to be minus 0. That's going to be our answer. For our f sub y, we're taking the partial of the function with respect to y. So we're taking the partial of 4x squared plus 5x cubed y squared minus 9y to the fourth with respect to y, equaling what? That 4x squared, same thing as a constant, that's just going to equal 0. 5x cubed y squared, same thing as the last one except with x this time. The x is just another constant multiplied by that y squared. Therefore, we just do the power rule as usual. We do 10x cubed y minus calc 1 right here. 9y to the fourth is just going to be 36y to the third. Those are our partials, and we can keep going with the partials. We can take double partials wherein we have the partial of x and y. That will be for a separate video, a separate topic when we talk about the chain rule. But as for right now, that is the simple partial derivative concept, what it means conceptually on a graph. And yeah, thank you very much.